to another exciting chemistry video. Today, our focus is primarily going to be on discussing physical changes and chemical reactions. The key here being able to differentiate between when something is undergoing a physical change only or whether something is undergoing a chemical reaction. So that's the overlying topic of this particular unit is chemical reactions, how we can identify them, how we can balance them, those types of things. So let's go ahead and look at our learning objectives. For this video, you should be able to differentiate between a physical and chemical change, balance any and all chemical equations, write out balanced net ionic equations, represent balanced chemical equations using particle diagrams, and explain how physical and chemical changes occur in terms of what types of bonds are being broken, and what types of bonds are being formed. So let's dive in. So let's talk about some changes in matter. A physical change occurs when a substance undergoes a change in its physical properties but not its chemical composition. So these are things like phase changes or potentially separation of mixtures. So you can see on the right hand side here, we have lots of different examples of changes in physical composition, in physical properties, but the chemical itself does not change. If I have a piece of paper and I tear it into two parts, it is still a piece of paper. I underwent a physical change, not a chemical one. In a chemical change, we're going to be breaking bonds and forming new chemicals. Speaking of chemical changes, these occur when substances are transformed into new substances. Now, how do we know that a chemical change has taken place? Well, there are several ways that we can identify chemical changes. For example, the production of heat or light. It might be an example of a chemical change. The evolution of a gas, the formation of a precipitate in aqueous solution, or a color change. All of these can be representative of chemical changes. So again, more examples here on the right of iron rusting, burning, cooking an egg, baking a cake, fireworks, electroplating, vinegar and baking soda. All of these are examples of chemical changes because we actually break bonds within the chemical and change what that chemical actually is and what it's bonded to. Now, chemical reactions must follow the law of the conservation of mass. What that simply means is that however many atoms I have at the beginning of my reaction has to be the same as the number of atoms at the end of the reaction. So what that means is that when we have a chemical equation, it simply must be balanced. Now, in order to balance it, we cannot change the subscripts because the subscripts determine what chemicals we are looking at. By changing subscripts, you change the chemical. However, we are going to change the coefficients, that is the numbers that come before the reactants or products in your chemical equation. That allows us to manipulate the equation, ensuring that we have the same number of atoms on the left side of the equation as we do on the right side, but also we're not altering chemical by changing subscripts. Remember that subscripts are determined through nomenclature rules, not through balancing of chemical equations. Don't forget those nomenclature rules. Very important to make sure that we write our chemicals correctly, our compounds and our molecules. Make sure that you recall Brinkelhoff as well. Remember your diatoms: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And again, we go through and we balance these equations by adding coefficients to ensure that the number of atoms on each side of the equation are exactly the same. Now, we'll dive into some more specifics on chemical reactions in a later video, but for today, I want us to focus on net ionic equations. These show only the elements or compounds or ions that are directly involved in the chemical reaction itself. There are other ions that are known as spectator ions that do not take part in the chemical reaction. So for example here, when I mix sodium carbonate with barium nitrate, it's going to show that I get two products. It's a double displacement reaction. However, the true net ionic equation, what actually changes is the barium and the carbonate ion react to form barium carbonate. You can see that through the changes in state. We had aqueous solutions, which ended up forming a solid precipitate in barium carbonate. So when we write out our equation, we don't necessarily see that very easily. So it's important to be able to write out net ionic equations. Well, how do we do that? Essentially, we break down our aqueous solutions into their constituent ions. So for example, you see that sodium carbonate in our total ionic equation is represented by 2 sodium ions and a carbonate ion. Barium nitrate is represented by a barium ion and 2 nitrate ions. Now, I would look at my solubility sheet to determine which of my products is going to be solid or not aqueous in solution. If it's a solid, those ions are together, they're not broken apart. So in my product side, I leave those together. So barium carbonate is a solid, it is not aqueous, so as a result, we're going to leave it as a solid. The sodium and nitrate ions are still aqueous when they're in solution. You can look that up on a solubility chart, or just know that all nitrates are always 100% soluble. So we leave those as aqueous ions in solution. We're only changing what reacts together to form the solid. So in our net ionic equation, we just simply cancel out any spectator ions that don't participate in the reaction. We have 2 sodium ions on the left, 2 on the right. Those are going to cancel out. And then we do the same thing with our nitrate ions. And what's left behind is our net ionic equation, where we had aqueous barium ions, aqueous carbonate ions, and reacted to form solid barium carbonate. So just to reiterate the concept in individual steps, the first step is that we are going to write out our full and balanced chemical equation. We then determine the states, which are typically going to be aqueous or solid, because we're primarily going to be looking at solutions. So we want to make sure that we are using our solubility chart as we go through and complete this. Soluble compounds will dissociate into their ions. Make sure you watch out for your coefficients and your subscripts. If it's something like CaNO3,2, you're going to have 2 nitrate ions. You also want to look for coefficients as well to determine the number of ions that are going to dissociate into solution. Insoluble compounds stay as a solid. We then are going to cancel all similar ions on each side of the equation and rewrite our balanced net ionic equation. So let's look at an example problem as a way to really make sure that we understand what we're doing. So let's go ahead and write out the balanced net ionic equation for copper 2 chloride and sodium phosphate. So our first step is going to be to write out our balanced chemical equation. So I've written out all the individual chemicals here using proper nomenclature rules. Again, if you need help with that, make sure to go back and check one of my other videos over nomenclature. Now I need to go through and balance using coefficients, and I went ahead and did that as well. I also labeled whether they are aqueous in solution or whether they are solid. Again, by utilizing a solubility chart, you can figure that out relatively easily. We then are going to write our total ionic equation. So we need to break these down into individual ions if they are aqueous, and if they are solid, we are going to keep them together. So I went ahead and did that as well. So if you notice, 3CuCl2 results in 3 copper ions and 6 chlorine ions. 3Cl2, right? So that would be 6 chlorine ions. 2Na3 is going to give you 6 sodium ions, 2 phosphate ions, and then I repeat the same thing on the right-hand side of the equation as well, keeping in mind to keep copper phosphate together. What I do next is I cancel all of my spectator ions, that is, the ions that are the same on both sides of my chemical equation. Once I have done that, now I go through and I write my finished net ionic equation. And if you followed these steps correctly, it should already be balanced, so you won't have to go back and redo that. Again, hopefully that makes sense. Make sure that you're following the individual steps that are listed, and you shouldn't run into any difficulties. Let's move on to the next part. Now let's talk a little bit about acid dissociation, because we haven't really talked a whole lot about acids and bases yet, and we'll talk more about that when we get to a later unit. There's a difference in how much of an acid dissociates based on whether it is considered strong or weak. Strong acids, what makes them strong is the fact that they 100% dissociate when you put them into solution, meaning that I get 100% of them to break apart into their individual ions. Weak acids and bases don't. So typically we keep those together in net ionic equations because weak acids and bases tend to dissociate less than 1%, meaning that less than 1 out of every 100 ions is going to dissociate into solution. Now, again, this is based off of something that is known as the Ka value, and again, we'll talk more about that when we get to that unit, but these are just a couple little things that I want to make sure that you keep in mind. We can represent reactions with particle-style diagrams. Now, we need to keep in mind the coefficients and the subscripts of the ions when we go through and draw them. We also need to keep into consideration limiting reactant, which again, we'll talk more about in a later video. But in this, notice that I have 2 hydrogen diatoms, 1 oxygen diatom, and I form 2 water molecules from that. So again, just making sure we're thinking about these things on a particle level and be able to represent them is very, very important. And again, we'll go through and discuss what happens if we have excess of one or not enough of another in a little bit later video. And lastly, what I want to focus on is the molecular difference between a chemical and physical change. Typically, chemical changes involve the breaking of the intramolecular forces. That is, the forces that are holding the individual atoms together in a compound. Those break and then are remade in order to form new compounds. So we're breaking the bonds that are within the molecules themselves. Physical changes typically involve the breaking of intermolecular forces, that is, forces that hold different molecules together. So for example, if I melt ice, It's still H2O. Ice is H2O and water is H2O. The difference is that I break the intermolecular forces that are between them, or if I turn water into steam. The compound is still water, it is still H2O. However, we change the state because we're breaking or making intermolecular forces between the particles. So I just want to make sure that you understand the difference of a chemical and physical change on what types of bonds are being made and what types of bonds are being broken. One of the key exceptions of this is dissolving of salt in water. This is typically accepted as a physical change rather than a chemical one, because once I remove and evaporate the water, I can get the salt back in its original form. So that's just one little weird exception that we like to have in the scientific community. So hopefully that provides a brief overview for you about the differences between physical and chemical changes. Hopefully you're able to balance chemical equations, write and balance net ionic equations, consider particle diagrams in chemical reactions, and explain how physical and chemical changes occur and what types of bonds are being made or broken. As always, I hope you enjoyed the video. Make sure you like, comment, subscribe, and we will see you next time. Have a great day. We'll see you soon. Bye-bye.